Well, we've been to Australia twice now through the years, and we've gone to 4 different cities. We've gone to Brisbane, to Sydney, Melbourne, Adelaide. And Andrew Brzezinski, he's actually with the Australian EPA. And I asked him, he actually is in Adelaide, and I asked him to come and speak here at our conference. Of course, normal conference year without the pandemic, he would have been here live and in person here in the Sheraton. But unfortunately, he's not. Although, here's the silver lining. Because here we are virtual, and he filmed a great presentation for you in Australia. And this is a presentation that he would not have been able to do if he was here in person. So, the silver lining of the pandemic, you'll know what I'm talking about. Watch his presentation.
G'day friends, my name's Andrew Brzezinski and I'm from Australia. Today I'm coming to you from South Australia in the Adelaide Hills, and I'm here at Animals Anonymous, and the reason I'm here is because I can't be with you in person. And I thought you might like to see something special from Australia that I can't show you if I'm in person. And today I'm going to show you some native Australian animals, and with me to start with is a tawny frogmouth. Have a look at this fantastic little bird. He's not to be confused with the owl, but he loves hunting. And this is Lois, who's a carpet python, and she's endangered in South Australia and actually comes from the state of Queensland up in the north of Australia. This is Australia's biggest huntsman spider. I can't believe I'm holding this for you. Great risk.
Just don't squeeze your fingers together.
That's all the spider you're getting for today. And this little fella on my left is a squirrel glider. He will glide up to 80 metres, and he's related to the... Oh, there he goes. But he's not a squirrel. And this is a goanna, and goannas of course make great bush tucker for the, particularly for the Aboriginal people who lived on Australian land for more than 60,000 years. And you can see he has a nice long forked tongue and beautiful skin. And this is a rufous, or a red bettong, and they carry their nesting material in their tail, and they're related to the kangaroo, but definitely not a kangaroo. Now this is a croc. This is a saltwater crocodile, and they grow up to be very, very big and very fierce. And of course they make great tucker as well, but you need to be pretty careful when you're chasing after these fellas. And these are the yellow-footed rock wallaby. They're very colourful, probably the most colourful in the world. And they are the biggest rock wallaby in the world. And this is Snuffles, who's a southern hairy-nosed wombat, but she'll grow twice the size of what she is now. This is the banded knob-tailed gecko, and he's from Western Australia, and he's a really small little fellow who never closes his eyes, but he cleans those eyes with his tongue. And finally, these are the Dunnarts. The babies are the size of a pinhead when they're born, and at the moment they're about a month old. Okay, so enough of the fun. My topic today is Australia accelerating or barely keeping up with the rest of the world? I'll let you decide as I run you through what Australia's up to. Today I'm going to talk about petroleum hydrocarbons, chlorinated hydrocarbons, PFAS, how we regulate site contamination, and our orphan site program in South Australia, and also research. But it'll be a bit of a fast run, but please keep up with me. First of all, Australia is 7 states and territories, and we have no national regulator. So all the regulation is done by each jurisdiction. And what that means is you can get inconsistencies, but over the last few years we've tended to be able to harmonise that problem, and we have quite a lot of national and state guidance, which has helped a lot. First of all, looking at petroleum hydrocarbons, it's fairly well understood, and it is well researched, particularly from CRC Care has done a lot of research in this space. They've done work with published a lot of technical guidance around natural source zone depletion, weathered hydrocarbons, MTBE, zero valent iron, and how it can be used for remediation, and so a whole lot of work around modest natural attenuation, biodegradation, and also around setting health screening levels for different depths, particularly for vapour intrusion. And you can see all of that work on the CRC Care website if you're interested. We have recently introduced in South Australia licensing for petroleum hydrocarbons for petrol stations, and this is seen to be a positive thing because most petrol stations will leak. And the licence conditions put the onus back onto the site owner or occupier or operator to do leak detection, and if they discover a leak, they must notify the EPA. And so we're hoping that this will result in a positive environmental outcome, and we'll pick up loss of integrity much sooner than what we would have previously. Of course, most of the tanks now are being removed, the old steel tanks, are replaced with the fiberglass tanks. However, there's always a tricky job. This particular job is some photos from last week, and a new proton therapy or proton accelerator machine is being constructed next to the National Health and Medical Research Institute here in Adelaide. And this is quite a first for Australia, and it's very exciting. The only problem is that the proton machine must be buried deep underground, and in doing so, old tar tanks are going to be excavated. And those tars are extremely volatile and are located next to the air intake of the existing Health and Medical Research Institute. So in order to do that remediation, a large tent with negative pressure is being constructed over the top of the old tar tanks, and you can see the excavators commencing work in there. I'll now move to chlorinated hydrocarbons. This has certainly increased a lot of our work in recent years. Previously, most of our work was petroleum hydrocarbons. Chlorinated is probably at least half the amount of work we do now. So chlorinated hydrocarbons are typically the result of closed industry or current industry. We're seeing a national decline in manufacturing, and unfortunately that leaves with it a lot of legacy issues. We see very large groundwater plumes that extend up to 2 kilometres or 1.25 miles out into suburban areas. The groundwater problem we can more or less manage. The risk from vapour intrusion, however, is somewhat more complex, and I'll explain how we go about doing that. So what we do is a bottom-up approach where we look at the soils first, particularly out in the suburbs, and we go out and explain to the community why the drilling program is occurring and how the information from the drilling program will feed into a computer model. We use graphics such as this and explain that the models have lots of parameters that go into them, and then ultimately we'll compare the results to levels which are set by our Department of Health as being safe or ultimately requiring intervention. And so we'll always do this in public areas first, and then if we find that the model predicts there's a problem, and we use quite conservative parameters when calibrating the model, then we'll look at moving into people's homes. We'll look at source removal or source treatment, and the best way to identify sources is with high resolution techniques. So we'll have a couple of drilling rigs in Australia for this purpose, and we'll deploy them to look at the sources. As we move into people's properties, we will start outside the home first, and we'll start at 1.5 metres below ground and look at the soil vapour in those spaces. It's important because we don't want interference from within the home impacting on our results, and you can get false positives, as perhaps you know. So once we've done the work outside the home, we'll have a look at subfloor. Subfloor sampling is usually quite reliable, much less variables than inside the home, and certainly it can give a reliable prediction of what might be happening inside the home, and either turn on or turn off the program. And we'll use Suma cans or radiellos. And here's some of the problems that we see once we move inside the home, and this is why we always leave the home to last. We had access, this is work done by EPA, we had access to a home in a suburb in Adelaide, and we had access for quite a while. And you can see with this slide the results of change in season. In the same room, you can see I've circled there 27 micrograms per cubic metre of TCE, and that was in winter. And then in summer, same room, 4 micrograms per cubic metre, which is pretty close to that too of safe. And it's a tricky discussion to have about which result is right or wrong. So these are some of the issues we need to contemplate when making decisions around what's acceptable inside the home. And then we looked at occupied versus unoccupied, and this was during the summer months. So again, you can see the effect of having a home which is occupied versus unoccupied, much higher results when unoccupied. And I guess this is showing what happens when the home's closed up in winter and the home's closed up when no one's there, compared to when it's opened up in summer and opened up when they're living there in that summer month of February. And then we also looked at different sampling techniques, and whilst we have confidence in Summa canisters and radiellos generally, here's a comparison of 20 odd in the home when using a Summa canister and less than 2 using the radiello. We're convinced that in this case the cans are dirty, and so we've taken measures with the labs to deal with that problem. But the issue here is trying to explain this result to the homeowner when that's the child's bedroom, and you've got less than 2 in one sampling technique and over 20 in the other sampling technique. And for them, of course, they will assume the highest result is what their child's being exposed to, and that's orders of magnitude above what we would want to see for a child. So in the end, the radiello was right, it was a dirty can, but the issue here is about using one technique versus another, and so it's important that you always use multiple techniques, and that's what we do now. And one of the other techniques which we've recently adopted, Blaine Hartman's has brought some gear out to Australia, and it's operated by CSI Australia. And this is the continuous monitoring, and we've found this to be exceptionally good value, and gives us a lot of really high quality data, and can deal with some of those problems around different times of the year and different techniques and different having to wait for lab results, and then people can know the results inside their home a lot earlier, or can make decisions around risk and further assessment a lot earlier. So being able to do that has great benefits, and we will be using this a lot more, I'm sure. Now, when we do have results above 2 inside homes, we've decided that mitigation should occur. So either the polluter will do that or EPA will do that. I'll talk a bit more about the Orphan Site Program. But so far in South Australia, the EPA, through its Orphan Site Program, has delivered 15 mitigation systems. And it's not too dissimilar to what happens in Northern America and Canada. But first for Australia, and we've got some really good outcomes here. We've been able to get every home below 2, and we've had some really high starting points. But importantly, we put memorials on titles, on certificates of titles, which bind the current owner and all future owners to keep the system turned on. So that's really important, and they have an alarm panel, and they can contact EPA if it fails. There's some pictures of the fans both in the roof space and outside the home. Putting systems in is not always easy. You can see here we don't always have the big crawl spaces like are available to the North Americans and the Canadians. In this case, you can see the timber floor was right on top of the soil. So that brings its own problems with installing these types of systems. And in this particular case, we couldn't get the system to bring the vapour concentration down. And we, in the end, sealed off every room and went into each room by room by room, analysing the vapour content, the TCE content, until we found one room, the laundry/bathroom, had a high reading, and this was what was increasing the vapour throughout the whole home. And we thought, wow, this is really strange for a tiled floor. You wouldn't expect to see vapour intrusion. Nonetheless, we moved the washing machine out the road and discovered this cover and sump, which was clearly open to the soil beneath. And this was the source of the vapour. So not every job's simple. You can always discover something which is contributing to the vapour that you haven't expected. So another problem we had was from noise from the system causing strange harmonics through the home. So in this case, we built a a whole vapour intrusion mitigation system in a building owned or occupied by EPA. And here we tested various mufflers, various types of plastic, various ends, various valves, various sizes, and measured the noise in a quiet room and until we could actually optimise the system to get the frequencies below the threshold of hearing. So this was good work. We discovered a lot about how the harmonics of mitigation systems work as part of that process. Now I'll turn to PFAS. PFAS, of course, is the chemical substance that keeps on giving. And it's certainly changed a lot of the work that is done here in Australia, particularly from a Commonwealth point of view or a federal point of view. And the reason for that is because the federal government owns a lot of land where PFAS has been used. And that land is typically defence land or airports land or ports land. And the tricky part here is the Commonwealth Government, as I said at the beginning, is not subject to any regulator, or environmental regulator. So the federal government's not subject to any federal regulator. So here the states have attempted to influence how this is done, but they have no jurisdiction, even though the land is within state boundaries. So that's had its own challenges. What we did in South Australia was we banned PFAS some couple of years ago, and that's been relatively successful. It has been quite successful. There's still 8 or so properties or premises that use PFAS or have approval to store it, not so much use it, and these are places which haven't been able to change to fluorine-free foams yet. Across the country we have a National Environment Management Plan for PFAS. It's quite a good document, and you can see it's available online at the website that I've put up there, at the URL I've put up there. And it covers off criteria for soil and for water and wastewater. It gives concentrations in eggs. It also gives concentration for protection of ecological species at 95 and 98%, both disturbed and undisturbed systems. So it's a good reference document for us, and it's working well, and it also deals with on-site containment and landfills as well. So it's fair to say that PFAS has caused a lot of anxiety and outrage in the community. You can see there's some headlines from various and photos from various outlets. And it still continues to be a problem. There's a company called Shine Noise who are continuing to try and engage with communities to establish class actions against the federal government and their agencies. Out at Edinburgh Air Force Base here in South Australia again, there's a whole soil remediation program happening, and this is being done by excavation and soil washing, and that's working quite well. There's some thought around bringing soil to here, which is PFAS contaminated from other Commonwealth sites, and washing it through this plant. So I'm sure there'll be more at future conferences spoken in relation to this plant. Similarly, they're doing some work with respect to groundwater remediation. Again, the sort of usual extract to the surface, treat, re-inject. A few problems with re-injection because we've got some pretty big volumes of water being withdrawn here. And typically the shallow aquifers in the Adelaide Plains, there's a series of shallow aquifers before you get into the deep aquifers 100 metres down. But mostly the shallow aquifers are the ones that are contaminated. And then landfill disposal is something that is not yet permitted in South Australia. A couple of the other jurisdictions will permit that. And what the NEMP, National Environment Management Plan, has set standards for disposal. We've adopted those standards for single composite lining systems and for double composite lining systems. You can see a double composite lining system being constructed here in the photograph down the bottom right hand side, and so that landfill has applied for approval to dispose of PFAS at that location. It's fair to say the community is not happy about that, so that's a process which is ongoing at the moment. All right, so moving away from the chemical substances now to perhaps some of the unique things we do with respect to regulation. And you can see here's a picture of, we have a what we call an annual auditors event. And auditors are people who are accredited by EPAs in each jurisdiction. And they are specialists in site contamination. They will have at least 10 years of experience, and typically as senior people. And the auditor must comply with the legislation when they're doing an audit. And the audit effectively is a review of the consultant's work. And the auditor forms an opinion of the consultant's work and an opinion on the suitability of a site for a proposed use. And the auditor's opinion must be unbiased, and the auditor must have no conflict of interest, and the auditor must not exclude anything or omit anything or include anything that's false or misleading, and must not have a conflict of interest. So they can't audit their own work or work of their colleagues or work where they've perhaps previously worked and had an influence. And so the consequence of not complying includes imprisonment. And so that's a significant penalty for this type of work. And I think perhaps the greater penalty is the loss of your accreditation if through malpractice. And so whilst we don't see that very often, the auditors are typically very good at what they do. It's a really good system to have that sort of reliable outcome which planning authorities and EPAs and site owners and future owners can rely on, the quality of an audit report, which is unbiased and unfettered. So audit system's really good. It's operating in most of the states and territories now. There's still a couple which don't have legislation, and they tend to borrow auditors from other states in a quasi way. The other thing which we've recently done, and this is similar to the professional engineers and professional geologists in the States, is we've introduced as a profession, we've introduced a scheme around professional certification. And what this does is it recognises site contamination professionals, which no one's ever done before. And there's really not a lot of schemes around the world as we looked around, as we developed this, which does this. So this is not regulated by the EPAs. This is a third-party scheme and run by institutes, professional institutes, and they are the ones who do the certification of the professionals. And then as an EPA, what we do is we recognise those schemes if they meet a certain standard, and we publish what that standard is. And then we expect the use of certified professionals in various cases, and we publish when that is. And then if we see work that's not up to scratch or is poor, we'll raise that issue with the person who's put their seal on the front cover of that report, and we'll talk to them about that. So, and then ultimately we would raise that with the certifying body if we continue to see poor quality work. So at the moment we're developing a policy around how we'll deal with standards and poor quality work, rather than just a policy on recognising schemes. It's that sort of next level down about the use of the professional and how they respond to that. So stay tuned, there'll be some more on that perhaps next time I speak. One of the other things we do in South Australia is, and this sort of goes back to the big TCE plumes that I talked about, is we have the ability to prohibit the taking of groundwater. And this is a powerful tool, institutional control. It allows us to mandate that people cannot use the groundwater. And really there's no other option but to do this. We don't want people accessing that shallow groundwater for irrigation or for any other purpose. Even bringing it into their home for their laundry or for their toilet could be a problem with the vapour that's associated with the chemicals that have been transported with that groundwater. So it's a great tool. Most people all people pretty much have access to reticulated water supply, so we're not taking the water supply away from them. And there's a penalty for non-compliance, and we're typically trying to do 4 per annum. And again, this is registered on their title or flagged against their title, so it informs all future owners of the property that groundwater prohibition area exists. Now I'll move on to the Orphan Site Program. This is something, again, which is unique to South Australia. And I guess I'm a little bit sorry, but I'm also biased that this is South Australian focused because I guess that's where I regulate, and that's what I know the best. But I certainly have a national view as well, and work on national programs. So we have an Orphan Site Program. We have a couple of $1 million Australian per annum, which is a considerable amount of money to spend on good quality consultants to do the work that we require to the standard we require. And this is mainly around those sort of sites where the manufacturing company has left and there is no person who we can require to do the work through legislation. So we'll typically look at human health risk. Haven't done a lot around ecological risk at this time, and that's what drives us, and we'll go in fairly quickly if we need to do that work. We only use consultants now rather than do it ourselves. We want to be at arm's length from the assessment work. We think that's best as the regulator. We commission the work and then we rely on the consultants to provide a report which is of high quality that we can give to the community. So we typically only do assessment, and as I mentioned earlier, we also do mitigation, which is really good because it means we can have a big picture discussion with the community about the beginning and the end. Typical questions from the community are, how will this affect my health? How does this affect my children's health? My neighbour's health? My neighbour has cancer. Is this why that happened? Is my home value going to go down? Why did this happen? How did the EPA let this happen? Who's going to pay for this? And is someone going to be prosecuted or punished for causing this? These are all really good questions, and these are normal questions that we experience when we engage with the community for the first time. So we see some pretty sad reactions, of course, and this is what we used to see. Now we have professional people who deal with the community on our team, and they go in first and they do some really good work, and we've got a great website there which I've described, and that allows us to smooth the waters and to make sure people understand what we're doing and why. And as I head towards the end, we've got some fantastic research programs happening here in Australia. We're looking at the microbes that live in the groundwater, Stygofauna, and how the different impacts from urbanisation has affected them. We're looking at how Indigenous people looked after the water in this country for 60,000 years and did a great job of it and really understood it. How can we embed their culture and their thinking and their knowledge into what we do? And this is a really important piece of research that's happening at the moment. CRC Care, you may or may not know about. Professor Ravi Naidu has led that for a long time, since its inception, and they've been extremely successful. And by rules, they must come to an end. So we're now looking to build a new CRC with Professor Naidu. I've recently led the Program 1 part of the bid, and this is going to be looking at risk and how do we do risk assessment, how can we change that and have the next generation of risk assessment. And this will be a significant part of the research into the next 10 years. So serious amount of money, as you can see. We hope the Commonwealth will equal that. That's the purpose of the CRC, and we're looking forward, hopefully, to success there, but we're still waiting to hear. Of course, we've just lodged that bid. Thank you. I hope you've enjoyed that. That's a race through what's happening here in a glimpse in Australia. Big thanks to Animals Anonymous again for the beginning of the talk, and I welcome any questions that you might have, and you're welcome to call me or email me, and hopefully I will get to see you all one day. Thank you.
Well, we have been to Hawaii 5 different times with our workshops. We always go to Honolulu, Waikiki, and honestly, one of our hosts has been Roger Brewer with the state of Hawaii, and he's been phenomenal to work with. I mentioned him earlier because he's also spent some time in China working with the environmental professionals there in China. But I was trying to find a map here, and if you notice, Hawaii is so small. If you have not been to Hawaii, you see on the map, I was trying to give you a global perspective if you're not exactly sure where it fits on the planet. But here we are. Hawaii is in that circle there. obviously in between Asia and North America. And so Roger Brewer is an excellent speaker, speaks at some of the biggest platforms and conferences in our industry. And so it's a privilege and a pleasure to have Roger here with us. So pull out your pens, get ready to take some notes, because Roger's got an excellent presentation for you.
Hello, this is Roger Brewer with the Hawaii Department of Health. It's a pleasure to join the Global 2020 EnvrioSummit virtually. The title of my presentation today is U.S. Environmental Investigation Assistance and Lessons Learned in the South Pacific and East Asia. When you live on a small island, then you're very reliant on outside technical support in your work. What I want to talk about today is our interactions over the past 25 years with consultants and regulators on the mainland and other places, how we've taken expertise that they have and compiled it for use in Hawaii. Then we've taken it to South Pacific Island areas and now in East Asia and applied it there. In some cases it works, in case it didn't, and how our practices have evolved over time to make the process more efficient, more effective. Well, there's too many references and acknowledgments to make over the past 25 years, 27 years, I guess, it's 1993. We've since then talked to people in every state, and regulators and consultants. One thing we discovered is if someone somewhere in the U.S. is an expert in the topic that you have a question about. We've also talked to people in Canada and a lot of other countries around the world. And we've taken their expertise and compiled it in our guidance, done some field research, modified it for use, tried to improve on it, and taken it elsewhere. I want to start with what I refer to as the great manufacturing shift. This isn't a surprise to anyone, I think. In the 1970s and 80s, it was a pretty widespread closure and cleanup of manufacturing facilities in the U.S. On the left is a picture of a textile mill in a small town in North Carolina where I grew up. At the same time, there was a huge expansion of manufacturing in Asia in the 1970s to 80s. A big decline in U.S. manufacturing, share of employment. A lot of this is due to automation, but again, a lot of it was just due to shifting of especially the more polluting manufacturing facilities to other countries. Let's shift ahead now to Asia in the year 2020. A lot of these big industrial complexes are being decommissioned and cleaned up, in part to address pollution concerns in the big cities, but also because these huge urban areas in desperate need of additional residential housing. So taking these old industries, shutting them down, moving them outside of the cities and building more modern manufacturing facilities. By coincidence, a few years ago, I was helping with a site up in northern China, a formal textile mill, and I asked them when it started, when did it set up? And they said, oh, in the 1970s, about the same time that the textile mills in the town I grew up were shutting down. I remember asking the owner of a textile mill in the town where I grew up what happened. And he said, well, we took all the machines, we packed them in crates, we shipped them to China, we opened the crates, we put it back together, we plugged it in, and we started up again. So a lot of the contamination problems we dealt with early on in the U.S. were just transferred to other countries, and we're dealing with them now. It's one of my favorite quotes from Confucius. So there are three methods to gain knowledge. The first, reflection, is the noblest. The second, imitation, is the easiest. And the third, experience, is the bitterest. So reflection I like to think of as research. Imitation is where we look at other people's guidance and try to adopt it for use in our situation. And the third, experience, is the bitterest. Maybe that's where we try to use other people's guidance. Some of it works, some of it doesn't quite work. We have to look for new directions. We get some of the lessons learned in the United States. And I like to keep the process simple. Step one, we characterize the site, identify the contaminants of concern, collect samples, and get data. Step two, we look at the data and carry out a risk assessment and identify any potential concerns and the need for remediation. Step three, we carry out the remediation. So I'd say for the U.S. in general, it's fair to say that we're world experts in remediation. So we're not going to spend a lot of time on that topic. But we've had problems, and we still have problems with issues like multiple remobilizations required to complete site investigation, overlook contaminants and potential environmental concerns, debates over final cleanup levels, and failed confirmation samples following remediation. And all these problems can cause investigation and cleanup to be delayed for years or even decades. And in the worst case scenario, we discover additional contamination following redevelopment. My favorite sayings from Carl Sagan: evolution takes place on the fringes of the environment, where the stresses are greatest and the need to change most urgent. So when you think of technology transfer to other countries, it's one thing we realize that it evolves as you do this. And a lot of these countries, island nations, have even more limited technical resources and time and funds than we do in Hawaii or in the US. So they're forced to evolve faster, better, cheaper methods to address these issues. So that's what I want to go over today. It's some of the approaches that have evolved over time as we've taken to other places. Let's start with risk assessment. I don't really like the term risk assessment for multiple reasons you hear me discuss. Here we describe it or use the term environmental hazard evaluation. The main document for reference, the evaluation of environmental hazards at sites with contaminated soil and groundwater. There are two editions. Hawaii edition we started in 1995, been working on it since. And then the more recent Tropical Pacific edition, we were contracted by US EPA to develop similar guidance, but more exclusive to US EPA standards and such for use in the tropical and the South Pacific. You see the reference for the web page there. You can download the documents. The Tropical Pacific edition is actually being translated into Chinese for use there and modified. Then we have recorded training webinars for environmental hazard evaluation. Look at the transfer or the evolution of risk assessment to risk-based screening levels. So in the early 1990s, when I first started in this environmental industry, then we had to carry out a site-specific risk assessment or forward risk assessment for every case we worked on. In this, you input your data, calculate risk. You can see in the equation below, health risk is calculated like excess cancer risk, non-cancer hazard, based on the average exposure concentration times a bunch of exposure factors times toxicity. Realized in the early 90s, mid-90s, you could rearrange this equation and calculate a risk-based screening level based on a target risk, like an excess cancer risk or same exposure factors and toxicity. This actually reduced the time to assess risk and just to identify the problems after you've collected samples from an average of 1.5 years in the early 90s. Now we can do it in just a few minutes. One of the problems with some of the early screening levels, and still with some screening levels, is they only address one or two concerns. And they may be important, like the US EPA regional screening levels, RSLs, they only address direct exposure. Well, that's a common concern you have to look at every site. But other concerns that we may need to look at include leaching of contaminants from soil and impacts to underlying groundwater, plant uptake of contaminants, ecotoxicity, contaminated soil, and we refer to as gross contamination, where you have heavily contaminated soil, may be isolated underneath the ground surface at the present, so it's not a risk. It may get overlooked in a risk assessment. Could cause a problem if exposed in the future. Similar problems for groundwater, drinking water toxicity, taste and odors, vapor intrusion concerns for both contaminated soil and contaminated groundwater. Another issue, discharge to aquatic habitats of contaminated groundwater or from industrial waste streams, of course. So we have to think about all these concerns and think about which ones apply to our site. When you're developing generic screening levels, you want to include as many of these concerns as possible up front. Leaching of contaminants and impacts to drinking water aquifers is a huge concern at small islands surrounded by seas, salt water. Here's an example from Guam, where the aquifer is fractured limestone with a very thin soil cover. We have screening levels we can apply to the soil. Two factors here, there isn't much soil in some places, and we know the screening levels are highly conservative. So as we start working in areas like this, we published guidance for use of laboratory batch tests, SPLP tests, to better assess the mobility of contaminants in soil. Also develop soil vapor screening levels for leaching concern. And so you collect vapor samples at depth. They allow you to estimate the concentration of VOCs and leachate as it's migrating downward. We're also working on lab-based soil column leaching tests, which should be much more accurate. The discharge of contaminated groundwater to aquatic habitats is also a big concern in island environments. The discharge of industrial wastewater, stormwater, and runoff shoreline areas is pretty well understood for overland areas, but big issue on islands is contaminated groundwater discharging on the shorelines. So next time you're in Hawaii or on a tropical Pacific island, hopefully, preferably with mountains, and go look along the shoreline, you'll see springs of completely fresh water bubbling up through the sediment. So that's a big concern, even if it's not a source of drinking water, for contamination of the sediment and benthic habitats. So we added to our guidance that the groundwater should meet aquatic toxicity screening levels at the point of discharge, maybe back off to acute toxicity in developed harbors and such. But at least we're looking at this issue. It's really important to work with local biologists, marine biologists. Then gross contamination concerns and short-term risk is especially related to petroleum and low toxicity solvents and such. Often ignored in risk assessments, a huge problem when you're redeveloping sites that is supposed to be cleaned up, and suddenly you dig into this contamination, you get very strong vapor emissions. And in some cases, causing short-term toxicity concerns, fire concerns, or just nuisance concerns. Again, a big issue for petroleum is not the BTEX, it's the TPH. We've added screening levels for TPH to our guidance. And again, you really need to identify these problems before you go out and start working on the site doing construction. Other potential concerns, if you're working in the South Pacific, abandoned munitions is a big concern. On Saipan Island, in just one spot in particular, the U.S. Navy left 50,000 artillery shells at the end of World War II and just walked off. They've been since removed in the last 10 years, but one thing we requested to do is add munition-related COPCs to the ESL guidance. You see different compounds there. The main concerns, of course, are explosions or misspelling hazards, but especially leaching and groundwater contamination risks, what the RDX chemicals like that pose for. In some parts of Asia, some agricultural fields are irrigated by partially treated industrial wastewater. There's heavy metal contamination concerns, especially for uptake into food crops. It's possible to develop plant uptake screening levels, but it's really specific to soil type, crop type, and you really need some expertise when you're doing this. So now we have a better idea of sort of common environmental concerns really need to be addressed up front in screening levels that are published and ensure that we're capturing all potential concerns at the first time. The good news is you don't have to reinvent the wheel. As I said, there's someone's an expert in every field I mentioned here. The US EPA has published for decades graded examples of risk-based screening levels and models and such. In vapor intrusion, we have our own guidance here. We identified some problems in EPA's guidance and have modified, fixed those for use in Hawaii and South Pacific and Asia. So we just take the screening levels from these or generate our own based on local factors. Leaching models, Massachusetts and several other states developed a semi-useful leaching model in the early 1990s that we still use. Massachusetts has done a lot of work with gross contamination they did early in the 1990s. Again, this flag let us know we're going to hit really stinky, smelly stuff. We could see it in the field. In aquatic toxicity, EPA has published a lot of screening levels, chronic and acute, as other entities have also. And again, ecotoxicity, plant toxicity, that usually does have to be more site, case specific, plant uptake. So once we have all these sources now of the screening levels, then we can generate screening levels for each one of these environmental concerns. I'm not going to go over that. Here's an example for RDX, one of the munitions-related contaminants again. You see lots of numbers, really useful, really confusing if you're a field person and you just want one number. So what we do in our guidance for the SALs is we take the lowest screening level, say for soil, and that becomes our final screening level. In this case, for RDX, the lowest screening level for soil is based on leaching, 0.01 milligrams per kilogram. So that's what you'd screen your data against. If you don't exceed that, you don't have any problems. If you do, you have to look more closely to see what specific problems are. Same thing for groundwater, the most conservative screening level, 0.71 micrograms per liter based on drinking water toxicity. And that becomes the final groundwater screening level. So you can see aquatic toxicity is much higher. Gross contamination, when can you taste RDX in drinking water? And believe it or not, people have done this, about 30,000 micrograms per liter, way above when it becomes toxic. Another thing you need to consider in the screening levels we learned early on to expedite the risk assessment process is you have to consider cumulative risk up front in the screening levels to avoid site-specific calculation of cumulative risk. and also use reasonable target risk for screening levels. So we typically use an excess cancer risk, 10 to the minus 6, 10 to the minus 5, sometimes for some chemicals, even 10 to the minus 4, to set screening levels for cancer concern. Hazard quotients for non-cancer concerns, we always start with a default of 0.2. That assumes that up to 5 chemicals with the same toxicity concerns could be present in the site. You rarely have more than that. So by using the screening levels, you're addressing cumulative risk up front. Maybe a little conservative, but it helps you expedite the process. One problem with EPA's RSLs, they have several tables, but the one most people use for non-cancer, it only uses the hazard quotient of 1. It assumes no other contaminants there, so you're not addressing cumulative risk. We have to make it easy to use also. Again, it needs to be fast and easy. A lot of people don't have that much training. So we prepared an environmental screening level surfer. We actually did this when I worked with California EPA. Thanks to Laurent for helping set this up. And this is a simple electronic lookup tables in Excel. You input the land use, groundwater utility, depth of soil, a few factors, site scenarios into this. Pick the chemical either by a chemical name or a CAS number, and it automatically generates that final soil screening level. And you can put in your own site concentrations. A little red X will pop up beside of it if you happen to exceed the screening level. It tells you, hey, you have a potential problem. You might want to look at it in more detail. And you get a few chemical specific notes like consider collecting soil gas, run lab-based leaching tests and such. So quick and easy now, we can identify a problem in 30 seconds. If you want more details, there are more detailed worksheets that give you the specific environmental concerns posed by that contaminant, even based on the concentrations you put in. And now you can look at that in more detail and see if it really is a concern at the site. There's some other worksheets also, a one-page summary report, one-page summary of toxicity and physicochemical constants used and target risks for risk assessors to look at, and a glossary of potential options for next steps. So that's the risk assessment process. I think we've done a good job over the last 20 years or so in the U.S. expediting this process, which addressed the concerns that we just talked about. Let's move on now then to really the big problem. That's site characterization. How can we avoid multiple remobilizations to complete a site investigation with no endpoint in sight, which is still very common, unfortunately, in the U.S. Failed confirmation samples following remediation after you thought you had everything done, and then this long years or decades of delay in finishing a project, or worst case, discovering additional contamination following redevelopment. Big problem, even in China especially, the environmental people are typically given 1 or 2 years to get in, characterize the site, and these are huge sites, clean it up and get out of the way before the developers get in. And if a problem is found afterwards, the regulator gets in trouble, not just the consultant. What's the primary source of the problem in the site investigations? Just to jump straight to the point, it's this reliance we've had on discrete soil sample data. By discrete sample, I mean you go to a single spot at a site, so you think an area is contaminated, you put a small handful of dirt in a 4-ounce jar, send it to the laboratory might try to mix it up. They call it homogenization, but you can't homogenize dirt. Ask any lab chemist. They test a random pinch or spoonful, and then you go with that data. The problem with that, anyone who's doing field work is familiar with, is you get conflicting concentrations reported for co-located samples, even laboratory duplicates. That's what you do. Well, typically you just take the highest concentration, cover your eyes, and move on. You think you've got the contamination well defined, you carry out your remediation, do your excavation, collect confirmation samples just to be sure, and no big surprise, some of the confirmation samples come up contaminated. Well, the first flag that should go up is you're comparing data for discrete points within an area to your screening levels. And all these risk-based screening levels was talking about apply specifically to the mean concentration of the chemical for a specified area and volume of soil, typically an exposure area. Look at the models, that's the way they're developed. They were never intended to be applied to single individual discrete masses of soil. So what's the problem here? Well, Dina Crumling, recently a child from US EPA headquarters, actually tracked down some of the original documents where the discrete soil sampling method was published. The environmental industry is the only sampling intensive industry that would ever do that, collect a random specimen really of something, put it in a jar and call it a sample. This is due to some of the early assumptions that were made. 1985 document, the level of contamination is assumed to be uniform within a contaminated area and 0 outside of it. So anywhere within that area, just test a pinch of soil, you get the same number more or less. 1989 document, when there is little distance between points, it's expected there will be little variability between points. So these are key assumptions, and this made it really simple. You can go to any place, just with a few discrete samples, identify the extent and magnitude of contamination. Where the sample is located, how it's collected was not that important. A key thing, though, is this approach was never tested in the field. If you read the original documents, they basically were saying, hey, we're just throwing this out there. There's a lot of assumptions. We assume people are going to look at this in more detail later. And it took 30 years, really. But there are a lot of warnings, even at the time, within and outside of EPA, that this may not be reliable. We actually went out to see if it is reliable. We carried out a detailed field study of discrete sample reliability several years ago. You see the paper that we published here. It's through grants funded by US EPA. We also have some field reports and webinars posted. We collected hundreds of discrete samples at 3 different sites. And at each site we designated 24 grid points, and around each grid point we collected 5 discrete samples, tested them independently, and then we had one of those samples or another sample tested 10 independent times at the laboratory to look at variability between co-located samples and within samples. At the arsenic site, it was related to wastewater from a manufacturing plant. We thought variability would be low, and relatively it is low. The total average variability between co-located discrete samples is 2-fold. This really could freak out some risk assessors when they see it, or even field people. Is the concentration 120 or is it 260? Well, it depends on where you take the sample. The lead site, this was lead contaminated in municipal incinerator ash mixed with fill material. We thought we'd see more variability, and we did. Average variability between co-located samples 7-fold. At this site, Hawaii's screening number for lead just happens to be 200 ppm. At every single one of those 24 grid points, we could collect a discrete sample that would be below 200 ppm, or we could collect one that would be above 200 ppm. So start thinking about the implications of that. PCB site, PCBs we know are terrible. Average variability almost 40-fold. This example here, 4.9 ppm in one sample literally 6 inches away, 2400 ppm. So think about all the implications of what's happened in your field work. One implication is discrete soil sample data can create completely artificial map patterns, especially small map patterns. This is the lead contaminated site. We simulated going to each one of the 24 grid points, collecting a single discrete sample, testing it, and making an isoconcentration map of the lead. We did that 8 times. You see these are 8 different maps for the same site. Imagine if 8 different people went out to the site and collected discrete samples. They look similar, but you start looking closely and the hot spots are bouncing all over the place, and even the cold spots are. Some of the large scale patterns in this case could be right, but these small scale patterns based on discrete samples can be completely random and completely artificial. So digging up sample points, done it plenty of times myself in the early days, it's a bad idea. Also problems for hidden error and risk assessments. These same sites, we had simulated collecting 10 random discrete samples and then estimating a mean and a 95% UCL for each one of those 10 sample sets. You see, statisticians are going to panic. If they see the mean is varying between separate samples sets for a site. And that's exactly what happened here. You see the mean varied by 2-fold or more, and down to PCB sites, well over 2 orders of magnitude, depending on which sample set you collect. So you never see this error in risk assessments because we never collect replicate sets of discrete sample for risk assessments. So all these key assumptions made for discrete sampling method early on turn out to be wrong. So contaminant concentrations are not uniform within an impacted area. They can vary dramatically over short distances. Individual samples, you can't homogenize them in the laboratory at the scale of laboratory aliquot and such. The solution to this, we're not going to spend a lot of time, is G sampling theory for particulate matter. He's written a book on it, goes into the statistical basis. It's been used in the mining industry for years. But the bottom line is the source of sample error related to the sample mass, compositional heterogeneity. It's a critical factor. Number of points included in a sample, not one, has to be multiple. How the samples are collected, how they're processed and subsampled at the laboratory. Laboratory analysis is the least error, even though we spend all our time on that validating data in the environmental world. Then replicate sample data is critical to test precision. There's lots of formulas and things on how to calculate sample mass and such. Gold miners figure this out early on because their job is to go to something like crushed ore, a body, collect a sample of it, estimate the actual mass of the commodity like gold in that ore body, and then you sell that to someone. So they progressively identify the errors over the last 100 years, and you see the results of poor sample data. Either underestimate the mean, overestimate the mean. Usually you're going to underestimate it, as they found out. Either way, you go out of business. So we took G-sampling theory over the last 15 years in Hawaii and been applying it in the field. We call this risk-based site characterization now. So you're tying it to your screening levels. It's referred to as decision unit multi-increment sampling methods. It's all published in our technical guidance manual. We have a 6-part series on how to do this, how to design a site investigation plan, sampling plan, how to apply this to surface soils, subsurface soils, excavation, stockpiles, sediments, VOCs, when to use discrete data, when are they potentially useful for screening or whatever. And now we're also applying the same approach to soil, water, and air, trying to get away from discrete sample data. The good sampling theory classes, Chuck Ramsey teaches a 4-day class. He's trained most of the people in the U.S. Highly recommended if you do environmental work. It's really shocking at first just how wrong your data can be. That's why it's 4 days. Francis Pittard also teaches detailed classes, mostly for mining industry. It's a real simple process. Step 1, you designate the area, referred to a decision unit, that you want to make a decision on. So the decision is an area and volume of soil targeted to assess risk like an exposure area or isolate contamination, optimize remediation. Think of it as an area volume of soil you dig up and send to the laboratory if you could as a single sample. Of course, you usually can't, so you're going to collect a representative sample from that area. We think of spill areas, exposure areas, and boundary DUs. We're trying to bound the contamination. Simple DUs here at Tinian Island, former housing complex. Here's the picture of the island. So here there were no suspected contaminant concerns at the site. It was 50 acres. The main concern was risk if there happened to be some contamination. Not that concern, so we just split it up into 4 DUs, 10 to 15 acres, kind of neighborhood scale size DUs, collected a sample from each one. And there are lots of adventures there. You'd be surprised what you find when you march back and forth across these areas in details. Might be big monitor lizards or unexploded bombs. Quite an adventure. These identifying DUs can be much more complicated. Here's a hypothetical case in China. There's a large former industrial complex, 50 acres. This site, first you split it up into areas of use, former office buildings, factory areas, former worker housing. Then you split it up into smaller and smaller DUs until you satisfy the risk assessors and the remediation people. If you look at the factory area, this is where you know you have heavy contamination. You split it up into really small DU areas to optimize your remediation both in the surface and in the subsurface. And in step 2, you just collect a representative sample from each one of these areas. But we're not going to do discrete samples now. We collect one sample from at least 50 points within the area, combine it into one large sample. There's 50, we call each point an increment. So it's a 50 increment, multi-increment sample. Minimum mass 1 to 2 kilograms. You have to very carefully process it, subsample laboratory for testing, test a minimum of 10 grams. Collect triplicate samples to test overall precision. And then now your field sample is representative of your targeted area, and your laboratory subsample is representative of sample provided. You'll never be able to say that with discrete samples. And again, this applies to subsurface soils, VOCs, everything. Step 3, then you've divided and conquered your site. This was one of the large manufacturing site we were working on in China. I mentioned it had been completely shut down because of confusion over discrete sample data. So we went in 5 days, 5 of us, designated 50 DU areas for sample collection, collected 60 plus multi-increment samples counting replicates, compared to pre-approved screening levels with rational screening levels. Used a portable XRF to screen the samples to expedite identification of areas to remediate. And we only had to go back, I think they had to go back 1 or 2 times to finish up the work, but in the end you had very high confidence in data representative and cleanup. So that's some new tools and toolboxes. We take our expertise from the US and expand it overseas or to other parts of the world where as Sagan would say, the stresses are greatest and the need to change most urgent. So these combined DU, MIS, ESL investigation methods, I think are a big improvement. And some of the methods are already in use in the US. Some of them, it's hard to implement new changes, like convincing people discrete sample data may not be that reliable, but it's easier in some of the newer environments. People are more eager to try these new methods. So that's it. And I know we may have a chance for questions during the conference. I'd be glad to talk with anyone. I always enjoy discussing new projects. And here's my email below. So thanks again.
Well, we've given you 9 different speakers from around the globe, 6 different continents that they were covering. And so hopefully it's been helpful and hopefully it's been educational. It's really some of the stuff that I've been learning as I've been traveling around the globe with our Enviro workshops. So I'm really glad that you've tuned in. Again, after the lunch break here today are the virtual breakout sessions, so make sure that you click on and jump into the rooms with some of the other speakers. And so here's the URL. Make sure you're saving your seat there in the virtual breakout session. Well, it's lunchtime here in the Sheraton in Charlotte, North Carolina. So we're going to take a break again, wherever you are in the world. Maybe it's dinner, maybe it's a coffee break. I don't know, but thanks so much, and we're going to take a break now.